Hello everyone, and welcome to session number 10 of this set of videos created to explore programming applications in reinforced concrete. In this session, I will present a Maple document that is capable of designing doubly reinforced rectangular concrete cross-sections. Doubly reinforced concrete beams have many applications. They come in handy when the architectural clearance limitations restrict the depth of the beam. They are also used to minimize the long-term deflection and to improve the ductility of a beam by allowing it to encompass more tension steel. They can also be used in zones where seismic activity or major wind direction fluctuations can lead to reversal of stresses. Let's now look at the Maple document, which is developed for the design of doubly reinforced rectangular concrete beams for flexure. This here is the region where the user is to insert the required input parameters. Let's go through them. The first one is the required factored moment. Then we have the initial diameter of rebar in tension and the initial diameter of rebar in compression. These are not necessarily the bars to be adopted at the end of the design process, but resemble a starting point. Next, we have the yield stress of the flexural steel and the compressive strength of concrete cover, and the diameter of stirrups. Since this is a template for the design of doubly reinforced beams, we will need the number of cycles required for the iterative procedure to calculate Fs prime, which is the stress in the compressive steel, in the analysis cycle that will immediately follow the design cycle to be performed. So here we need to specify the number of cycles required. Next, if the tension steel at midspan is to be extended to the support section to be used as compression steel, then the user can insert the diameter of the tension steel at midspan, and the document will design the number of bars to be extended from midspan to the support section. If the tension steel at midspan is not known or is not yet designed, and the user wants the document to design the bar diameter in compression at the support section, the user can insert a 0 value for dB prime, and the program will find the optimum diameter of bar to be used in compression. Next, the user is required to define the range of bars to be used for tension. Here we have 9 different bars, and thus we will have 9 different design alternatives. The user is also requested to insert the range of the bars to be used in compression, where only the optimum bar in compression will be designed, and that bar will be used in the 9 design alternatives of tension steel. Then the user needs to define the design economy parameter, which is nothing but the design strength divided over the factored moment presented as a percentage. If the depth of the beam is already known, then the user can insert a value for h given here. And if the depth of the beam is to be designed by the Maple document, then the user can insert a 0 here and specify the length of the beam center to center, as well as the support conditions of the span to be designed. There are 4 different alternatives for the span type, which are simply supported, one end continuous, both ends continuous, and cantilever. Similarly, if the width of the beam is known, then the user can insert a value for the width of beam. If the width of beam is to be designed by the Maple document, then the user can insert a 0 here, and the width will be taken as h divided over 2. Let's use the parameters shown on screen to run our first example for the design of doubly reinforced rectangular concrete beams for flexure. Please note that in this particular example, the user has inserted that the diameter of bar in compression is to be 18 millimeters. Let's run the document by clicking on enter. The output file is generated. Let's look at the design sections one by one. Here we can see that the depth of the beam has been decided to be 550. The width of the beam has been taken as h/2 and corrected to be 300 millimeters. These here are the design alternatives, where you can see that for each design alternative we have a different bar diameter in tension, but for all the design alternatives the diameter of bar in compression has been predetermined and predefined as 18 millimeters. You can see that some of the design alternatives did not satisfy all the required conditions, and some did. From among those that did satisfy the required conditions of the design, only one section is chosen as our chosen or design section, for which a full cycle of analysis is performed in order to make sure that the section is adequate and that all the assumptions that we have made are correct. Then the cross-section is plotted with dimensions, and the ductility status of the beam is shown on screen to indicate that the beam is in the tension-controlled zone. Let's go back to the input parameter zone and change the diameter of bar in compression to 0, indicating that we do not want to specify a diameter of bar for the compression steel, and we want the Maple document to design the diameter of bar in compression. Let's click Run. We can see here that the diameter of bar in compression has been selected by the Maple document as 12 millimeter bars. Some of the design alternatives passed, some of them failed. Again, a section is chosen among these that passed as our chosen section with a full cycle of analysis and the cross-section and the ductility figure. Let's say that the user does not want to specify the bar in compression, but at the same time does not want to use certain bar diameters in the design process. So we can come here and say from the bars 12 millimeters to 20 millimeters, I don't want them here and only consider these alternatives for the compression steel. If we run the document, you can see here in the matrix that the diameter of bar in compression chosen is 22 among the set that we have specified for the document to choose from. Again, one section is chosen as our design section, a full cycle of analysis, the cross-section, and the ductility status. Let's go back again and this time return those that we have deleted and change the boundary condition for the span from both ends continuous to one end continuous, and run. We can see here the different design alternatives, the chosen section, its plot, as well as the ductility figure. In such a case that the depth of the beam is already known, then the user can specify the value for the depth, let's say here 600, and run the document. You can see that the depth is now 600. Same process is carried out. One section is chosen with its plot and its ductility figure. If we go back and change this time the width of the beam from 0 to a specified value given by the user as 250 millimeters and run the document prepares the required design. Now the depth is 600 specified by the user and the width is 250. These here are the design alternatives. Only one of them passed the required conditions. So that section is chosen with a full cycle of analysis, and then it is plotted and we show the ductility status of such a beam. This concludes this session. Thank you very much for being with me again, and I hope that I will see you in subsequent sessions. Best wishes.